Y'all, we're on to a new chapter, a new topic today. We talked a fair amount about the force stuff. We're going to talk about some more forces here. Trust me. But at some point we have to move on. So we're going to be looking specifically in this section, in this topic, at circular motion. And not just any circular motion, it's one specific type of circular motion. This is uniform circular motion. Any thoughts on what that might mean, uniform circular motion?
Yeah.
That right there? Okay, well, that's true. This is an example of uniform circular motion, but what makes it uniform?
It's the same.
Same, okay. What's the same? Okay, that's true. That's true. We could be a little bit more information though. So no, the thing is though, you've nailed it. You've absolutely nailed it so far. So we can notice something else that's the same here. Okay, that's true. That's true. That actually ties in with circumference. What else is the same here? What else? The speed, yes, exactly. See, you got it. So yeah, it's the speed that's the same. So when we say uniform circular motion, it means that we've got something that's going around at a constant speed. So that's the thing that uniform really means. It's moving at a constant speed. Usually I have some kind of fancy, from the textbook image on the title page of these things. I chose my own this time. So I don't know if any of you guys have been on one of these rides, something like this. Yeah. Did you all have harnesses or some kind of belt on? Fantastic. I'm glad to hear that safety is still the number 2 priority. That's a lot of fun, right? You get in this thing, you're standing against the wall, it starts spinning, and all of a sudden you're going up the wall because of the forces involved. Actually, it's pretty cool. We'll maybe look at analyzing this at some point as we talk through this particular topic. So that's a real life example of uniform circular motion. Once it gets going up the speed, it stays at that speed. Here's another example. And let's see, I'm going to go ahead and play this. It'll probably mess up everything I'm doing with Zoom right now, but I'm going to do it anyway. And then I'll deal with the consequences later. All right. So I don't know how loud this. What language is that? It's English. Okay, all right. So that's enough of that. Okay, all right, there we go. So back over here. So yeah, that is another example of once they get going at constant speed, uniform circular motion. And if we wanted to, we could go through and analyze that at various points as that person was circling around and figure out the forces acting on his body. Maybe we'll do that. I don't know. We'll see. We'll see what we end up doing. But before we do anything in terms of analyzing those, that's great. Can we get rid of this? There we go. Okay. We need to define our terms and talk about some basics in this type of motion. Uniform circular motion, as we said, means that we've got an object moving around at constant speed in a circular path. This could be my ball that I'm swinging around here, and I'm trying to keep moving at constant speed. It's hard to do when I'm swinging it in a vertical circle. but it's a lot safer for me to do it in a vertical circle than it is if I were to swing it around over the top of my head in a horizontal circle. This thing slips sometimes, it comes untied. So if I start spinning this around this way, keep your eyes open, because you might have a ball soon. All right. So uniform circular motion, we've got an object traveling at constant speed in a circular path. All right. So we've defined that. Let's look at some of the math involved. About the speed of our object. Let's see. We know that what's speed equal to? Back in chapter 1, chapter 2, what did we say speed? Yes, yeah, speed is distance over time. Thank you very much. Yeah, speed is distance over time. And so if we think about the distance that an object that's moving in a circle travels when it moves around one time, well, the distance around a circle is what? Circumference. So for one trip, this would just be the circumference over the time for one trip. Let's write this as time for one trip. Do you all remember the formula, maybe learned in 6th grade, something like this, for the circumference of a circle? Yeah, 2 pi r, yeah. It's also up there on the screen, right? Yeah, so, but you didn't need that though. She didn't need it, just to be clear, y'all. I'm not very obvious. She didn't need that. So 2 pi r. So that's the circumference of a circle. And then the time for one trip, we give this a specific name. We call this the period. And period we represent with a capital T, which is exactly what you see up there on the PowerPoint slide. So the period is the time it takes for an object to travel once around a circle. Period is the time it takes for an object to repeat one cycle of motion. Specifically with circular motion, it's one time around a circle. So V is equal to 2 pi r over t. All right, so I've got an example here that I'm going to do. This says conical pendulum example. So let's get out of this, stop that, dance around, whatever. All right, so I need somebody to actually time me this time, and I'm serious this time. I actually do need a timer. Anybody want to time me? Thank you, Brandon. I'm going to start swinging this thing around in a circle, and I'll let you know when to hit start and when to hit stop. Okay. On 3, we'll hit start. As soon as I actually get this uniform. 1, 3, 3, 4, 6, 7, 8, 9. Good. All right. Thank you. I just need it. Obviously, we're kind of crude example a little bit, but it'll be good enough for us to learn a little bit about this type of motion. All right. So it took, you guys, first off, let's talk about what I was doing. 14 seconds, right? So I'm swinging this ball around, something like this. There we go. And you can see that the path that the ball is actually taking is that it's tracking out a horizontal circle. At least that was my goal anyway, for this thing to be moving in a circle in the horizontal plane. And the reason I've got that meter stick on the table is because I was trying to measure, the diameter of this circle. So I was doing my best to try to keep the diameter of the circle at a meter. I was mildly successful. I struggled a little bit, honestly, but that's all right. That's what we'll use for the diameter of our circle. So for this example, the diameter of our circle was what? 1 meter. And let's see, we went around 10 times. So we traveled around our circle 10 times in 14.2 seconds. So from this information, I want to figure out, well, what's the speed of the ball? How fast is the ball? Right, well, we can do this. I think about that equation that we had up, the period T is the time for one trip. Time for one circle, one trip, whatever. Let's see, 14.2 seconds for 10 trips would give me there's 1.42 seconds in each cycle, in each circle. So it took about a second and a half to complete the circle. The radius is going to be, well, let's see, half the diameter. Diameter is 1 meter, so the radius is going to be 0.5. And now, we can just plug in the numbers. No worries. And I got a speed of something like about 2.2 meters per second. That's what I got. You guys agree with me? You all good? All right. So there's my little first example of uniform circular motion. I said we call this a conical pendulum. Let's see. Any ideas on why we would call this a conical pendulum? Yeah, because of the string. You look at the string and this, the fact that there's a circle at the bottom, and the string and the ball kind of form a cone as we complete the motion. So therefore conical. And pendulum. What's a pendulum? Yeah, something that swings back and forth. Thank you very much, Seth. So we basically have something that's cycling back and forth in a circle. But yeah, so therefore conical pendulum. That's why we call this particular example what we call it. But I'm not sharing multiple screens. It's not my intent to. That's interesting. Let's just go back to here and hope that works. Yeah. All right. So there was my conical pendulum example. And now I've got one for you guys. Yeah. So anybody happen to know who these people are? Randy Orton. Oh my gosh, somebody knows. Yeah. Oh, well, and I was all excited. Now I'm disappointed. Okay, so yeah, it's right. Okay, this is Randy Orton right there. You didn't know that beforehand? No. Okay. All right. I'm a fool. All right. That's all right. Yeah. So this is Randy Orton here. He's being spun around in a circle by somebody who apparently is not his friend. If you guys want to watch the video of this, it's right there. So you can go to PowerPoints, click on it, do whatever. I'm not gonna play it. Sorry. So it says, let's see, he's being spun around in a circle, and I've given you a couple pieces of information here on the screen. It looks like from where he's being held to his head is 1.37 meters. And it looks like from where he's being held to a point that's at the same height as his head is 0.65 meters. It says that, and I counted this. This is real data. And as a matter of fact, I looked up these people's heights and all that, and did the whole looked at the body charts of what proportion of your body goes from here to here, and so on and so forth. You guys maybe have seen stuff like that, like how long is your arm in comparison to your height, this type of stuff. Yeah. But yeah, so these are good numbers, the best I could get anyway. It says he spins around once every 1.4 seconds. So your task is to figure out, well, given this information about the geometry and about the time for one cycle, how fast is its head moving? So when you get an answer, let me know. The other guy's name is Cesaro. So yeah, if you wanted to know. Your forearm is as long as your foot. I did not know that. I might have known that at one point, but unfortunately, if I don't use information just like everybody else, I don't retain it. So.
It's a good way of like seeing the.
Oh yeah, yeah. Of course now. Yeah. Okay, as fun as this is, we need to focus on the problem at hand. So let's do that. Always change your answer if you want to change your answer. Fingers. Got you both. Probably. Gracie. Yep. Kristen? Yep. One, two, okay. Caitlin? All right, I'm waiting on, I think, one or two other people. Got you good? Did somebody not bring a card today? Did I get everybody? Okay, I'm missing somebody, but I know who all's here, so no worries there. All right. Let's see. The most popular answer was C. Nobody picked B. The correct answer is D. So the correct answer is D. So let's see what happened there. So I'm just gonna what am I gonna do here? I'm gonna write down what we've got on the screen. 1.37 meters there, and let's see, 0.65 meters there, and the period is 1.4 seconds. And let's see here, our formula says that speed is equal to 2 pi r over t. And there's a reason why I gave us this conical pendulum example before I asked you guys this question. So when I do this conical pendulum right there, and if I were to be able to freeze this at one moment in time, say right now, I look at what's going on there. Well, I basically have a triangle here. I've got a triangle where the string forms the hypotenuse, where my meter stick is at the bottom of it, and then a line connecting my fingers down straight down to the meter stick would be the other side of the triangle. So that's what I've given us up here, where the radius of the circle that Randy Orton's head actually tracks out right there. So you think about the circular motion, that circle that his head tracks out is in the horizontal plane. So we need the radius of that circle. We don't need, for instance, the slant of the cone or anything like that. We need the radius of the circle that's in the horizontal. That's always, I assume that's most of you guys probably use this for your R value rather than figuring out what I've got there. All right. Okay. So let's do that real quick. If I Pythagoras my way through this, 1.37 meters. I wonder how happy Pythagoras would be if he knew that his name was used as a verb. About that, the impact you have in your lifetime, and here's somebody whose name has lived for what, 2,500 years. Incredible. All right, so rearranging this. Of course, if you look at the actual mathematical development, somebody actually did it before Pythagoras. But whoops, there we go. Sorry. But he knew about his contribution first. So therefore he got it. All right. All right. So there's the radius of my circle. 2 pi times 1.21 meters over 1.4 seconds. Should give me the result that hopefully gives me the result that I had circled in red. Now my speed looks like 5.41 seconds. Go ahead, Brian. Oh, yeah, it's meters per second. Thank you. Meters per second. Thank you very much. All right. Anything here, guys? All right, we get the misconception that tripped a lot of us up. Yeah, okay, good. All right. Okay, so let's move on here. There we go. It's fantastic. Wish that thing would go away just a little bit quicker than it does. All right, so speed's constant in uniform circular motion. We've talked about that. And so we might think, and I would certainly understand thinking that, well, if the speed is constant, that means we don't have any acceleration at all. But that's not true. That's not true. So the speed is constant in uniform circular motion, but the velocity is not. So remember, when we talk about velocity, the velocity has not just size information, not just magnitude, but it also has direction information. So when we talk about velocity, velocity is a vector. It has both size and direction. So the size of my velocity is not changing, but the direction is. For this circle that we've got tracked out on the screen here, at one moment in time, my velocity looks like it goes to the right and up a little bit. And at the next moment in time, it goes to the right and down a little bit. So even though the size of the vector has stayed the same, the speed has stayed the same, the direction of the vector has changed. And anytime we have a change in velocity, we have to have an acceleration present that's causing that. That acceleration is going to point along the direction of the change in velocity. And it seems like by bringing up acceleration, I've actually skipped on to the next slide a little bit. We don't have to necessarily remember this pretty picture and be able to explain it or anything like that. The main point here is that even though speed is constant, velocity is not. Velocity isn't constant because, hey, look, the direction of the velocity vector changes. So objects can be moving with constant speed and accelerating. The direction of the acceleration, when we've got an object moving at constant speed in a circle, always points towards the center of the circle. Right. This acceleration is it's given a specific name. It's called centripetal acceleration. Centripetal, another fancy word. Centripetal just means it points towards the center of the circle. Yeah, that's literally what centripetal means. It's inward pointing. So yeah, that's in towards the center of the circle. This centripetal acceleration will have a value we can calculate if you know the speed of our object, the speed of our ball, and the radius it's tracking around in. Centripetal acceleration is equal to v squared over r, speed squared over r. Always points towards the center of the circle. So this entire chapter, we just deal with stuff moving in circles at a constant speed. Later on, chapter 8, we'll deal with things changing speed as they move in a circle. All right. So this centripetal acceleration, as I said, is what causes the object to change direction. It's what causes the change in direction of our velocity vector. Velocity vector stays the same length, but changes direction as this object tracks around in a circle. Okay, anything here, guys? All right. Let's see here. So I pull out another example problem. It says we've got a bobsled track. Fantastic, nice canned problem. That's all right. It says we've got 2 turns in our bobsled track. We've got one that has a radius of 33 meters and one that's got a radius of 24 meters. And what do we want to do? We want to calculate the centripetal acceleration at each one of these turns if the speed stays constant. Speed stays at a constant 34 meters per second. So this is kind of easy peasy. This is just to get our feet wet. Let's see, can I do this? On. This is fascinating stuff. All right. So let's see. This is yeah, not much to this here. We'll see. There we go. A sub c is equal to v squared over r. Our speed is always 34 meters per second. Squaring that, divide by the radius of the first turn is 33 meters. And when I do this, it looks like my acceleration is 35 meters per second squared. That's great. Okay. So we can certainly go ahead and do the other one. Again, this is going to be v squared over r. Into it, just getting our feet wet. Getting familiar with our equations and also seeing kind of possibly an interesting result to think about. All right. You like my stylus? Yeah, right there. We see that as this thing goes around the first turn, the 33 meter turn, it's got a centripetal acceleration of 35 meters per second squared. And then what happens? Well, as it goes around this second turn, yeah, we'll pick up maybe right there, maybe at that specific spot, maybe that's the spot we're interested in. As it goes around this second turn, maybe this is the spot we're interested in there, points towards the center of the circle, something like this. But for this second turn, it's a smaller radius, but we end up with a larger acceleration. So we think about this. For the first turn, bigger turn, we get 35 meters per second squared. A second turn, smaller turn, we get 48 meters per second squared. So a larger acceleration. Does that check out with what you guys have experienced in life? Can we think of any kind of comparisons we can make to this with something we might have experienced? Yeah, awesome. When you're driving, you're going around curves. If you take a shallow curve at 55 miles per hour, it feels a lot safer than if you take a much sharper curve at 55 miles per hour. Yeah, and that's because of the accelerations involved. Okay. Awesome. That's exactly the connection I was hoping to make. Okay. Good. Questions there, guys? Okay, let's see. Clear all drawings. Fantastic. Boom, boom. Let's hide this. And let's move on with our lives. Okay. All right. Great. There we go. It's all worked out. That's fantastic. That's better than my finger, but whatever. All right. So how about this one? It says we've got an object that's moving around in circular motion. So there we go. And then at some point, let's see, this object is let go, is released from its circular path, is what it says there on the screen. And we're asked the question, well, does the object continue to move in a circle, or does it just kind of go along in a straight line? What do y'all think? Yeah, a straight line. Now, if I let go of this ball, it's going to happen, right? So we'll time this correctly. Heads up, Brandon. Okay, all right. So I got it into the floor a little bit, but it certainly didn't keep going around. Like, no, of course not. Yeah, it's just going to go travel in a straight line. It's pretty sure I'm going to hit you, but I've been wrong before. It's happened. Yeah, I had that ball come off of a string once. The student's hand, just like that. I was like, wow, that was amazing. Yes. Try to avoid that. All right. So yeah, no, it's you take away the thing, you take away the thing that's causing the, yeah, there we go. You take away the thing that's causing the acceleration to happen, the string, and it's not going to move in a circular path anymore. Awesome. Right, so, okay, maybe talk about this maybe next week. I don't know. Maybe some other time. Okay, so if we have an acceleration present, we have to have something causing that acceleration. So in order to have an acceleration present, here we go. We have to have something causing that acceleration. So we have to have some force or forces causing that acceleration. So a net force that causes a centripetal acceleration is what we're going to call a centripetal force. So we talked a lot about forces in the last chapter. We talked about different kinds of forces. We talked about normal forces and tension and friction forces and weights and so on and so forth. So those are specific types of forces that are caused by specific interactions that I just mentioned, normal force, so on and so forth. Centripetal force or acentripetal force is not a new type of force. It's not like, oh, I got some new interaction that's causing a centripetal force. No, the centripetal force here, there's my ball. The centripetal force here is caused by the tension in the string. When we talk about centripetal force, we're not talking about a new type of force. We're just saying what direction it points in. So, last chapter we talked about forces pointing in the x direction, forces pointing in the y direction. When we talk about centripetal force, it just means that we're talking about a force that points along an axis that's connecting our object with the center of a circle. So this just means that we've got a force that's pointing, radially either into or out of our circle. Towards the center of a circle or away from the center of our circle. All right. So we certainly saw Newton's second law. We said that the sum of the forces in the x direction is equal to mass times acceleration in the x direction. A lot of that in last chapter. We've got Newton's second law again. That just says the sum of the forces in the centripetal direction is equal to mass times acceleration in the centripetal direction. And looking at this, and maybe at some point I will remember to do this, I would actually love to have a sigma in front of that F. So, to stress the fact that, hey, we're summing up all the forces that act in the centripetal direction, just like we summed all the forces that act in the x direction or the y direction in the last chapter. It's not a new kind of force. It's just we happen to be talking about the direction the force points in. Okay. All right. So let's see. This is an important point. You can tell. Look at how big the letters are. So it says for circular motion problems, we always make sure to point one of our axes towards the center of motion. Went through all those steps for solving force problems. The second step was choose X and Y direction. Well, when we choose direction for force problems where we've got an object moving in a circle, we choose towards the center of the circle to be one of those directions. Let's see how much time. Creative here. I guess if I don't want an answer, I shouldn't talk to myself. All right. So we've seen this slide so many times, right? Same slide. Nothing new there. Okay. All right. So let's go back to Randy Orton. I would like to know what is the size of the force that his neck actually has to exert on his head to keep his head attached to his body. So that, that's my goal. I mean, you spin something around like this, somebody around like this, how much, do we have to worry about this kind of thing? How much damage is being done? So on, I don't know. I'm curious. So I would like to know that. We figured out that his head is moving at approximately 5.4 meters per second squared, or meters per second, 5.4 meters per second. And I want to know the size of the force that his neck must exert on his head in order to keep his head attached. So I want you guys to help me out. Draw a free body diagram of Randy Orton's head. So draw a free body diagram of his head. Look at his head. Think about all the forces acting on his head. Where is his head, making contact with the outside world? What are our long-range forces? And see if we can come up with a free body diagram for his head. I see Kennedy, Claire, Bianca. Hey, Kayla, Caitlin, Elena. Okay, Elena, Kristen, yeah, Katie. Right. Got a couple more of you guys. Good. All right. Okay. So we got a little bit of work to do here. That's all right. So let's see. You guys did not, just to be clear, did not like this question at all. Free body diagram of his head. What's the long range force acting on his head? Gravity. Yeah, weight. Yeah, I heard somebody say gravity. Yeah, so there's a weight force acting on his head. Straight down. Weight of Earth on, I don't know, H for head, I guess, whatever. Okay. What point of attachment does his head have with the outside world? Yeah, neck. And let's see, which way would the force that his neck is exerting on his head point? Yeah, if I read you correctly. Yeah, this way. All right. Let's see. What could we call that force? I don't know. Maybe it's a tension force. Whatever. I don't really care. We can call it tension, I guess. Tension of neck on head. Are there any other points of contact between his head and the outside world? No. That's it. That's it. Yeah. So the only place his head is touching the rest of the world is at his neck. So that's the only contact force we could have. And then we've always got the long range force of gravity. All right. So the correct answer here was C. Was choice C. Okay. Any questions there, guys? So 3 of y'all picked that one, just to be, so yeah. All right. That's okay. That's all right. There's no normal force here. His head's not on the ground. So a lot of us probably put a normal force on there, but his head's not on the ground. So therefore, no normal force. All right. So the correct choice is C. Let's see. Let's see what we can do from here. All right. So our question is to figure out what is the size of the force that his neck exerts on his head. That's our goal. Figure out what is that tension. Step 1, draw a free body diagram. Step 2, decide on X and Y directions. Instead of calling it X, let's call it C for centripetal. Why not? Decide on X and Y directions. Step 3, any forces that don't act in the X and Y direction, we have to break up into components. The weight force, awesome. It acts in the Y direction. The tension force there is an oddball. It has a piece, I drew that in a bad place. It has a piece that acts along the centripetal direction and a piece that acts along the Y direction. There's my axes again, guys. Sorry about that. Okay, so I've done step 1, step 2, step 3. Step 4 is Newton's second laws in the C and Y directions. So along the centripetal direction, we've got mass times centripetal acceleration. All right, F equals ma. Only force that I have acting along the centripetal direction is that C component of that neck force. Let's see, and then M, this would be the mass of his head. Centripetal acceleration is V squared over R, so we can go ahead and fill that in right there. Anybody know the mass of a human head? What's that? 10 pounds. Are you serious? No? Okay. All right. Does anybody know the mass of a human head? Any thoughts? Let's see. Don't Google it, because then the FBI will know that you've been looking up the mass of a human head. So let's see. There we go. We've got some nice scientifically sourced information here. 4.5 kilograms or about 10 pounds. Very good. Yeah. Very good. All right. Oh my gosh. Okay. So anyway, so 4.5 kilograms is the mass of a human head. So T sub C is equal to, time to throw these away. I will pick that up. I will not leave that for custodian. Absolutely not. I would not do that. Just to be clear. So 4.5 kilograms. We figured out that the speed here was 4.5 meters per second. Okay, and earlier we figured out the radius of the circle, right? 5.4. 5.4. Earlier we figured out the radius of the circle, right? What was it? Yeah, this was 1.21 meters. Thank you. 21. So from this, we can figure out, let's see, that the size of the C component of that tension force. This looks like 108 newtons. That's 108 newtons there. We have the C component. All right, we've done the sum of the forces in the centripetal direction. Come on, let's look at the Y direction. Sum of the forces in the Y direction is equal to mass times acceleration in Y. Is his head accelerating in the Y direction at all? No, it's moving around in a horizontal circle. That's 0. On the left-hand side, we've got T sub Y pointing upwards and W pointing downwards. T sub Y minus the weight of his head is equal to 0. So it looks like T sub Y is going to be equal to the mass of his head times gravity. This looks like 44 newtons. Great. Now that we have the components of our tension force, we can certainly go ahead and Pythagoras our way to the overall size of that force. And this looks like it's about 117 newtons. There we go. So that's enough force to lift and hold 12 kilograms. Not horrible, but certainly, you got to think about this kind of stuff. If you pick up a child and you're swinging them around, guys, when you do that, make sure you do it by 2 arms. Okay, never by 1 arm, because you can do some serious damage, actually long-term damage. And be careful with that kind of thing. Yeah. Yeah. Yep. Yeah. I would like to have like 2 more minutes there at the end, so I could talk a little bit more about that. But
She made me really scared to have children.
yeah, you pick up a toddler and swing them by 1 arm. There's absolutely damage that you can do in here where you cut the growth of the arm for the rest of your lives.
I have both my sisters walked from doing that. If I had a neighbor, don't think by my parents.
Yeah, it's fun until it's not fun anymore.